Today we're going to look at the following circuit problem. What happens when we plug this forcing function into this RC circuit? As you can see, this forcing function is a type of square wave. It has a height k volts above the zero, sort of the zero position here. So it has an amplitude of k volts. And then as you can see, it also has a 50% duty cycle, so it's on half the time, off half the time, and it repeats with a period of tau. So it will repeat an integer multiples of tau, tau, 2 tau, 3 tau, etc. When we plug this voltage into the circuit as f of t, we then want to find out what happens right here, v of t. We want to find out what happens at this node here, which represents the voltage across the capacitor. This is an RC circuit, a first order circuit. So let's begin. The first step is we're going to try to write a differential equation using Kirchhoff's current law. So Kirchhoff's current law tells us that the current into a node has to equal the current out of a node. So if we look at this node here, we can use Kirchhoff's current law, which will tell us that the current into the node, how can we represent that current? We can represent it as the voltage difference across the resistor divided by the resistance. So that's going to be f of t minus v of t divided by r. So Kirchhoff's current law tells us that the current into the node, which is this, has to equal the current out of the node, which is going to be the current through the capacitor, this current. And based on general formulas, we know that the current through a capacitor is going to be the capacitance times the derivative with respect to time of the voltage across the capacitor, which is going to be v of t minus the voltage here, which is grounded, so that's 0. If we rearrange this differential equation, we find that RC dv dt plus v equals f of t. This is the linear first order differential equation we're going to be working with. So let's apply the Laplace transform now to every single term in this equation. Note that the Laplace transform can be applied term by term because the Laplace transform is a linear transformation. So let's apply the Laplace transform here. If we do that, we're going to find out that RC times S v of s minus v of 0 plus v of s equals the Laplace transform of the forcing function. If you're confused as to how I got this, you can look up a Laplace transform table online, just Google images. You can follow along there. So we now have this equation, which is now just an algebraic equation. It's not a differential equation. But note, it requires us to know an initial condition, v of 0. It requires us to know the voltage across the capacitor at time equals 0. How can we reason through what that might be? Well, let's use just simple logic and simple equations. So we know that before time equals 0, the switch is open. So that means, obviously, without anything being plugged into the circuit, the voltage across the capacitor must be 0 before time equals 0. Here's 0. Here's the voltage across the capacitor. Here's time. So we're on the left-hand side, we're always going to be voltage 0 before time equals 0. And then let's imagine at time equals 0, the voltage jumps up to some value and starts changing then. So we have this discontinuity. Actually, I'll put it like this. We have this discontinuity at time equals 0. So imagine that happens. Well, what does that imply? That implies that the slope here, that the derivative of the voltage with respect to time is infinity. Infinite slope, vertical line. What does that then imply? Well, recall that the current through a capacitor is equal to the capacitance times the derivative of the voltage with respect to time. Well, if we know that the slope of the voltage is infinity, that implies the derivative is infinity. That implies that then the current is then infinite at that point, which of course is impossible. You cannot have infinite current flowing through a wire. Not possible. So therefore, any discontinuity at time equals 0 is also impossible. At time equals 0, there can be no discontinuity. In fact, the voltage across the capacitor at any time cannot have a discontinuity. It must be continuous, or else we suffer from an infinite current. So therefore, the voltage across the capacitor always must be continuous, just based on sort of simple physical constraints. Therefore, we know that at time equals 0, the voltage must be 0 with the principle of continuity. So we can then allow this initial condition to go to 0 just based on that basic logic we just used over there. So then we can, of course, isolate v of s now more easily. We're going to find that v of s then times src plus 1 equals the Laplace transform of the forcing function. And finally, this implies that 1 over src plus 1 times the Laplace transform of the forcing function equals the Laplace transform of the voltage at the node of interest. Let me just erase this over here in case we need some extra space. So now the only thing for us to do is to find the Laplace transform of the forcing function, this function here. Well, before we do that, let's just represent this function in the time domain, not even in the Laplace domain. And then we can sort of go from there. So how can we represent this function in the time domain? Well, hopefully you understand that we're going to need to use Heaviside step functions to represent this forcing function. If you're not familiar with the Heaviside step function, it's represented as u of t, and all it is a function that's 0 before t equals 0, and at t equals 0 it turns on in a way and jumps up to 1. This is the Heaviside step function. Open circle at 0, closed circle at 1. That's not super important, but this is the Heaviside step function. So we're going to represent this infinite square wave, infinite pulse wave with sort of as an infinite sum of Heaviside step functions. So let's go ahead and do that. So let's represent f of t as an infinite sum from n equals 0 to infinity of, well, we know that the Heaviside step functions have to turn on, boom, 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 at integer multiples of the period tau. So let's turn on the step function at integer multiples of the period tau. We are allowing n to vary across the integer, the field of integers. So this is how we represent this Heaviside step functions always turning on at integer multiples of tau. But then we also note that the forcing function turns off at odd multiples of tau halves. Here it turns off at 1 tau halves, at 3 tau halves, at 5 tau halves, etc. So let's now represent that like this. This is now going to turn off at odd multiples of tau halves. Let's then close the summation off there. So notice that I represented odd integers as 2n plus 1, where n is allowed to be any integer. We, of course, could have equivalently represented odd numbers as 2n minus 1, but note what would have happened in that case. If I plugged in my lowest index to here, I would have gotten -1, so t minus -1 would have been t plus tau halves at my lowest index. This would, of course, implied this is a type of Heaviside step function that would have had something happen before t equals 0, which it would have turned off before t equals 0, and then it would have sort of turned on, etc., etc. That is not how I defined my forcing function over here. As you can see, my forcing function is defined. The way it's defined, nothing happens over here before t equals 0. That's because the switch doesn't close until t equals 0. So this is not possible. That's why I did not use 2n minus 1. It's just to make the indexing work out correctly. If that doesn't make sense to you, why I use 2n plus 1 to represent the odd numbers and not 2n minus 1, pause the video and convince yourself why that was necessary to allow the indexing here to work out correctly. So now that we have a representation of the forcing function in the time domain, let's apply the Laplace transform to this forcing function and find it in the Laplace domain, in the frequency domain. Recall that, again, the Laplace transform is a linear operator, so it can pass through a summation and be applied to these terms individually. Using the Laplace transform table, I know that this is going to be the correct representation in the Laplace domain. 1 tau halves s. I believe that's correct. 1 over s e to this, and negative n tau s, negative 2n plus 1 tau halves s. Okay, so now we have the representation of this forcing function in the Laplace domain. So now we're going to plug it in over here into our representation of v of s in the Laplace domain. So let's just do that down here. Oh, and I did forget one thing. I also wanted this forcing function to be able to have an arbitrary height k. So actually, I did forget something. In order to just allow this to be more arbitrary, I'm just going to put a factor of k in front of here. Notice that because the Laplace transform is again linear, the k just comes along for the ride here when we take the Laplace transform of both sides. But this k will just allow us to set an arbitrary height for our, for our sort of input function. So we're not just restricted to allowing k to be 1. We can let k be anything now. So that just makes our solution a little bit more generalizable to any square waves you might encounter. So let's go on here. We're going to plug in that forcing function representation into this representation here. I'm actually going to put k out front, src plus 1, and then I'm going to have this whole thing here. I'm actually also, when I plug in this this huge infinite sum into this equation here, I'm also just going to factor out the 1 over s factors. I'm going to factor them out of the summation as well. Multiplication is also a linear operator, so multiplication can pass through a summation as well. So I'm going to just factor those out there, and I'm going to put them out there as well, and then I'm going to have negative n tau s minus e to the negative 2n plus 1 tau halves s, close the summation. Okay, so now we're almost done. Let's just take note of what we have here. Let's call this function of s, which is then being multiplied by this infinite sum, let's call this g of s. And so then if I just, I'm now just going to do this as a thought experiment to help us find the solution, to help us think about how we can better find the solution. If we call this, and what's in parentheses here, g of s, if I distribute g of s into the summation, I eventually find that v of s is going to be n equals 0 to infinity times g of s e to the negative n tau s minus g of s e to the negative 2n plus 1 tau halves s, close the summation. Okay, and then if I apply the inverse Laplace transform to both sides, that's also a linear operator, so I can just apply it inside the summation term by term. Then I'm going to find that v of t is an infinite sum, n equals 0 to n equals infinity, of, and then again, just use your Laplace transform table online to solve this. This is then going to be the inverse Laplace transform of g of s itself, but then we're going to include some shifts here. So we're going to shift it by n tau, and then we're also going to include a Heaviside step function, and then of course we're going to include another g of t, this time shifted by the odd, sort of the odd terms in the series, and then we're going to include another Heaviside step function over here, t minus, this is going to be t minus 2n plus 1, tau halves, close that parenthesis, and then let's close the summation overall. So this is going to be the final answer, and as you can see, the only thing we're left to find is actually going to be little g. We just need to find little g from big G, and then we can apply little g inside this sort of final expression and get our final answer. So how do we find little g? Well, we just need to invert this back into the time domain, invert the thing in parentheses here. Well, how do we do that? Well, all we need to do is use partial fraction decomposition right here. Before I do partial fractions on big G of s, I just want to also just make this expression look a little nicer. I'm going to factor out an RC from the denominator of this term. So I'm going to pull out an RC here, divide this by that, and then I'm going to divide that 1 by RC. So now let me just do a partial fraction decomposition on these two terms right here. So I know I have 1 over s plus 1 over RC times s, and now I want to decompose this into two separate fractions like this. Now you can use whatever method you want for doing partial fractions. I'm just going to do my own personal favorite method, which is to multiply both sides by the denominator on the left-hand side. That leaves us with this. Boom, clearing the denominator on the left. Now, again, you could do whatever method you want. You could group like terms. That might be a little extra work. My method of choice is to realize that this function must be valid for any real value of s, or actually, in fact, probably any imaginary value of s, or complex value of s, but it has to be valid for any value of s I could insert, and that includes very convenient values of s. So what if I choose the convenient value of s equals 0? Well, that's going to make this term vanish, and I'm going to find that b is equal to rc in that case. That also means it also has to hold this equation for the convenient value of s equals negative 1 over rc, which is going to make this term vanish, and which is then going to imply that 1 equals a times negative 1 over rc, or which implies that a equals negative rc. So that's an easy way to find these two coefficients, those two numerators there. So this then implies that our g of s here, actually, this implies that our g of s is then going to be, it's going to be k over rc times the quantity negative rc over s plus 1 over rc plus rc over s. Perfect, that is my partial fraction decomposition that I wanted. Notice that the rc here is able to cancel these rc's in the numerator. Perfect. That's even easier. That makes my expression even nicer than I wanted. And so then finally, if I just come here and invert the Laplace transform over here, so I want to now find g, little g, in the time domain, I find out, actually, let me just write this over here if it's going to be easier to see. I'm going to find out that little g, using Laplace transform rules, is going to be k times the quantity negative e to the negative 1 over rc t plus 1. So this is going to be the little g that I was after, and again, I just found this using a table of Laplace transforms. If you're confused on that, again, just Google a table. So now all that's left is I just need to apply this little g of t to this final expression up here. So let me just give myself a little space on the board to do that, and then we'll have our final answer. So let's apply this little g of t that we see down here. So that's going to mean that my final answer for the voltage across the capacitor is going to be n equals 0 to infinity k of, I'm actually going to flip the order of the terms in the parentheses there, so I'm just going to make that a little easier for myself to understand. E to the negative 1 over rc, and then instead of times t, remember I got to apply the shift based on a Laplace transform rules. Close that parenthesis. Perfect. That's how we do that. That's going to be this first term in the first term inside the summation, and then for the second term inside the summation, let's just do the same thing again. So that's going to be minus k times 1 minus e to the negative 1 over rc, and then again, it's not just t. I have to apply this shift, which is going to be a little bit more involved, which is the odd numbers times top halves. Close that parenthesis, close the big parenthesis, and then apply my Heaviside step function shift as well. And then let me just close the summation overall. And then also just notice that I can take out these factors of k, factor these out of the summation as a whole. So I'm just going to bring the k out there so it's a little easier to read for me. So notice that this should be the final expression. We have these exponential functions and these Heaviside functions, and they each just have the necessary shifts to sort of make all the math work out correctly. This is going to be our final solution here. And so I just want you to notice a few things. So a lot of you are probably wondering, well, why is the final solution an infinite sum? Had we actually solve this differential equation another way, just use the method of undetermined coefficients or use variation of parameters to solve the differential equation, for each individual interval of the forcing function or something like that, obviously we would not have gotten an infinite series or an infinite sum for our final answer, it would have just been sort of a finite number of terms had we done this other method of solving the differential equation just sort of piece by piece. So you're thinking to yourself, why is there an infinite sum in our final answer here? And the answer is this is not really an infinite sum, because think about what happens when I plug in an arbitrary time value, like time equals 5 seconds. Well, if I plug in time equals 5 seconds here, I'm going to get 5. I'm going to plug in, I'm going to plug in 5 into an infinite number of terms. But as n increases, after a certain point, 5 minus n tau is going to be less than 0. This is going to overwhelm the 5, bringing these terms the terms inside the Heaviside step functions to less than 0, which is just going to turn off a whole bunch of the terms in the infinite series. So for any arbitrary t, there's only going to be a finite number of terms turned on in the infinite series, again, for any arbitrary t for any given time. So that means that this is not, in fact, a true infinite series. You can rewrite this in a way that gets rid of the Heaviside functions and gets rid of this infinite limit. You can actually just compress this into a smaller, nicer looking summation, which is a finite sum. And of course, that's more of a mathematics exercise. As engineers, I think it's just more appropriate to plot this function as it is and just get some graphs and take a look at what happens to the voltage at the node. You don't need to actually go through the mathematical exercise of condensing this down unless you want to. A few just other final thoughts. If you are going to plot this function in MATLAB or Desmos or something like that, you can choose, you might be wondering, how do I choose my finite value up here, for any, how do I just choose this limit, because I can't use infinity there. I can't have the computer compute infinitely many terms. And the answer is, well, let's say that you want to plug in, the highest number of t that you want to plug in or that you're interested in is 500 seconds. Well, what terms are going to end up mattering there, and what terms in the infinite series are going to be turned off at 500? Well, if I plug in 500 to this Heaviside step function, for example, I'm going to get 500 minus n tau, and these terms are only going to matter if the internal guts of this function are greater than 0. So if it's less than 0, the terms aren't going to matter anymore. So I'm going to have 500 has to be greater than n tau. And that means that 500 over tau has to be greater than n. If n surpasses 500 over tau, the terms all flip to 0 and they don't matter anymore. So I think an appropriate limit for the top here, if you're only interested in t equals 500, would be something that's close to 500 over tau. Of course, you might also have to take into account this term, this Heaviside function over here. But I think this should be a good sort of a good starting point. And notice that then if I use this upper limit, all the terms I need will be turned on will be present in the infinite series. And so therefore, the answer I get for the answer that this is going to give me, the graphs that this is going to give me, are not just approximations of the solution. They are going to be the actual solution, because I have used every single term that I need in the infinite series. I have taken all the terms that are actually going to be turned on, and I've just discarded all the ones that are going to be turned off by limiting my limit here. So by limiting this upper limit here, using a finite thing, you are not in fact just approximating the solution. You're actually, for your interval of interest, you're getting the exact solution. It's not like a Taylor series where you're only approximating it. This will actually be the exact solution for the interval of interest. For example, here restricted to time equals 0 to 500 is the interval of interest. And then the other thing I also want to note is this is super important. If you plot this function on Desmos or MATLAB, I would recommend putting absolute value bars here and absolute value bars here. Why is that? Well, number one, you can. It's not going to affect anything, because if this is going to be a positive term always, because imagine what happens if this term was negative. Well, if it's negative, then that's just going to turn the function off using the Heaviside function. So if there ever comes a point where the absolute value bars would actually affect the solution and turn a negative number positive when it should really be negative, that doesn't matter because this is just going to be turned off. So number one, we're not affecting anything by putting the absolute value bars here, so it doesn't matter. But so then you're saying, well, if it doesn't matter, why are we doing it? Well, it's important for the exponentiation to always be a negative number, because even when the Desmos or MATLAB realizes that it needs to turn terms off, it's actually it's not going to just sort of recognize that this is 0, and it's not for the terms that it turns off and recognizes that this Heaviside function is 0, it's still going to go about computing this huge expression here. It's still going to go about computing this. It's very inefficient, but it's still going to do that for the terms that are 0. Well, for the terms that are 0, this is going to be a negative quantity. So for the terms that are 0 without the absolute value bars, this would be a negative quantity. Negative quantity times this extra negative sign is going to be a positive quantity. And of course, e to a super positive number is going to be really big, really big. And then you're going to get an overflow. So MATLAB and Desmos will not be able to compute this. So even though it's getting overflows for terms that really should not be turned on, it just doesn't, it's not smart enough to know that it doesn't need to compute this. It will still go about computing the terms that will eventually be zeroed out, and it won't be able to compute them because this will be negative, so the overall e to the positive number, it will be e to the positive number, which will be really big, so it's going to give you an overflow. You can avoid that by just putting the absolute value bars here, and then even for the terms that are 0, when it goes about computing those, the coefficients of those terms, computing the thing in these parentheses, it's not going to have an overflow because this will ensure it's always e to a negative number. Same thing over here, put the absolute value bars. It's not going to have any practical difference mathematically, but computationally, it will allow MATLAB and Desmos not to have these overflows of sup e to really big positive numbers. So definitely, if you plot, just be careful about this upper limit here. Make sure that, if you're interested in, 500, you make sure that this upper limit is going to be 500 over the period. And then make sure that you also put these absolute value bars around there to avoid these overflows, which is sort of, again, MATLAB and Desmos are awesome tools, but they're not smart enough to sort of disregard the terms that are going to be 0. They go about computing the coefficients anyway, even if the final thing turns out to be multiplied by a 0 step function. Thank you for your time.